Welcome. My name is Alexis Koulidis, and today I will give a general overview about drilling engineering with the perspective of the technology and the methodologies that are utilized in drilling. And this is going to be the first video from a series of videos that I will create depending on the interest. So the title of today's presentation is Applied Drilling Engineering, the science behind exploiting the Earth's energy potential. Now, when we talk about anything related to subsurface, which relates to excavation, ants are the most efficient miners. So we can learn a lot from nature from the perspective of how those small insects are able to create those stable structures. But what is interesting to see is when the ants, they are creating these tunnels, so when they do their colonies, we can observe that they can now feel with their small legs which grain is actually vibrating, and then they can sense which grain actually to remove and create a stable structure, but also decide which direction to dig in. So the Earth has a circumference of approximately 40,000 kilometers. Now this is the US estimates, as I mentioned, and in the US they are drilling approximately 135 kilometers per day. Now if you take this into perspective of a year and assume that this is a good average, it gives approximately 50,000 kilometers drilled every year. The energy demand now is significantly increasing, of course, due to several reasons, and it's going to be around 50% increase by 2050. Drilling now is not only for extraction of energy, but it's also many scientific reasons. This is a very interesting project that is happening in China, is which they're drilling now the deepest well of approximately 11,000 meters, and of course this is for scientific purposes and also to discover some additional reservoirs. Then of course another very interesting is called the Mantle Drilling and Observatory. This is from Jamstec, in which they are planning to drill now a well in which they will hit the Moho zone. So Moho zone is now the interface between the crust and the mantle, and we want to see from what actually material is made, and of course obtain additional information regarding our planet. So those are very interesting facts about drilling. This is the table of content for what I will talk today. So firstly, a little bit about background, history of drilling, drilling techniques, assessing the subsurface. Then we will go to some challenges that we are facing currently regarding geothermal. And I will end the presentation with future videos that I'm planning to do. So terminology, what is actually drilling? And drilling is a destructive action that requires a tool, which this tool we're gonna see later on is called a drill bit, but now the technology is actually moving forward, which you might not really need a drill bit, maybe in several years from now, to create now a cylindrical borehole. And the main aim now is you want to reach a target depth 100 meters, 200 meters, 5 kilometers, it doesn't matter, but as safely and as most cost effective as feasible. This is a graph which we can see now on the y-axis, the number of wells per year. This is US. The cost per well, millions, and the drill footage per well per year. And you will see that the wells drilled is actually quite fluctuating. But what is interesting to see is that the cost per well and the drill footage per well is actually increasing exponentially. So in the US, the average drill footage per well is approximately now 15,000 feet. So we are talking for wells that they have mostly very long horizontal section. Now, of course, drilling is not something new, and actually in ancient China, they have a very interesting drilling technique approximately 2,000 years ago, in which mostly they utilize now to drill a small well. You can see here the wood, which they use a percussive action, which means you're hitting now the wood hard in the ground in order to create wellbore. And the main reason for this was the search for salt. And salt, for this period of time, you're using it mostly for preservation of meat. Now, interestingly, why we're actually drilling now, cylindrical boreholes. So it's not only that is the most effective way to provide rotation, but it also comes up from Leonardo da Vinci approximately 1500 AC, which he created a device. So you can see here, this is a wood, this is the wood holder to keep it stationary when you are drilling it, because now from related to torque, you don't want the wood also to rotate, rather only your tool. So you're rotating the tool, and they realize that if the wellbore is actually cylindrical, it reduces the collapse of the wall, and they use this for water pipes. Very interesting fact. But then this is, I would say, one of the most famous patents in drilling industry, which is from Howard Hughes, and is the first rotary drill bit. So this is a roller cone bit, and the patent you can see is from 1909, which now this really revolutionized the drilling technique, the way that actually we are breaking the rock. You can see these roller bearings. So the roller bearings are actually, so this is a 2-cone bit. And this actually, as you rotate the entire structure, those roller cones, they actually also rotate by themselves, destroying the formation. Then a little bit more historical information regarding drilling at the early 20th century. So we start having the American Petroleum Institute standards, and then in 1955 we have the first well drill from a drill ship. So what has happened now over the last 30 years? So drilling is the same, but over the last 30 years we start using drilling fluids design in hydraulics. Then we have horizontal multilateral drilling, so complex wells. It also includes the extent ridge drilling wells. We start becoming much more sophisticated, corresponding to sensors. So we have logging and measurement while drilling instruments downhole. The drill bits that we are using, so we have the polycrystallic diamond drill bits. This is actually from the 1970s that they have been introduced. Then we have the ultra deep water wells, and of course geothermal drilling. And this is now an image from TU Delft, in which they drilled 2 deep wells in order now to extract heat from the subsurface. So let's go now to well construction. And drilling, I would say, is a very sequential action. So first we're always drilling a section. Then depending if you are on the surface section, intermediate, etc., you log it to obtain properties of the formations. Then you run a casing. We will talk about what is a casing and what is a cement. Then you place the wellhead at the surface. Depending again in which section you are, you may run a cement bond log and you might test the shoe. So this is the cement shoe to see that the integrity is actually there. And then you just repeat. You go now with a smaller drill bit, you drill again a section and moving forward until you actually reach the target depth. Now, the deeper you go, as I mentioned, it means you need more power. And more power, it comes from the mechanical action. So you need to rotate now kilometers of drill string, which means you need big motors at the surface in order to provide rotation. Now, in the same time, when you lower a casing, you pull up equipment. This is heavy. We're talking about hundreds of tons. So those structures, they become bigger depending now of the weight and the mechanical power that you need to put in order to reach your target depth. Of course, we circulate fluids, so the pumps are getting bigger. Now, this is a conventional land rig, and we can see now a semi-submersible drilling rig, which is for offshore applications. Now, those are, I would say, technological masterpieces. What are the main equipments now from the drilling rig? Now, so this is the drill pipe. So the drill pipe is what connects everything together. And we go with, you have the drill. And the use of the drill pipe is, of course, to circulate the fluid inside, but also to provide all this mechanical energy to the drill bit. So to provide rotation and torque to the drill bit. To do that, we use a big motors at the surface currently, so it's called top drive. Before we were using the Kelly bushing, and at the same time you have the pumps which they pump the fluid now from the surface, from the top drive in your drill string to go at the bit to clean now and be circulated out from the annulus back in the surface. In the cell shakers, there is additional equipment such as desilters and desalters to remove now the fine and the coarse cuttings from the drilling mat, and then you circulate it back. The essential systems now in order to have drilling is the hosting system, so to move now the string or any components such as casing, circulation and solids, we discuss about them. Rotating equipment, we also talk about the top drive and the Kelly. Then you have the well prevention and control. This we're going to talk in another class. Monitoring. Of course, those rigs are now instrumented, so there are several sensors across the drilling rig in which you are measuring, and of course the power unit. So all those components, they need now power in order to operate. And from well construction perspective, mostly we have the conductor casing, which is the first layer, the unconsolidated formation. So you want to seal those formations because those are unconsolidated, so easily to fail. You don't want also to pollute the groundwater aquifers. Then we go to surface, intermediate, production. Now, the deeper we go, those formations, they're porous. Might be high porosity, might be low porosity, but there is always fluid between the grains, as we can see here in the image. And depending now on the environment, you can have a normal pore pressure regime, so you have the hydrostatic pressure, but depending now on several circumstances, there are zones that might be overpressured. So it means that they are higher from the hydrostatic pressure. And then there are also zones that they are under pressure, which means they are lower than the hydrostatic. And this pore pressure regime is very important to drill any kind of well, because it assists you to drill those wells safely. So when we're gonna talk later about the drilling fluid, the main action of the drilling fluid is to provide hydrostatic pressure in the borehole, in which this pressure is higher actually than the formation pressure. In cases lower, then you have a negative delta P, which means now that formation fluid can enter in the wellbore. So of course, when we talk about the pore pressure and fracture pressure, it's mostly related now, of course, with wellbore design. So how actually you can drill those wells successfully. So pore pressure, we talk about it. Now fracture pressure is the minimum pressure to initiate cracks in the formation. Now, as you are drilling, you have your drilling fluid, but of course now the fracture pressure is not always linear with depth. It also fluctuates significantly depending on the lithological circumstances that this formation has encountered over the years. And what it happens now is that in case your drilling fluid pressure exceeds the fracture pressure of the formation, so then you artificially crack the formation and you start losing fluids. And this creates now many challenges, because once you start losing fluids into the formation, an excessive loss of hydrostatic pressure, then the pore pressure will become higher, and then you can have again problems with well control. And this is again the main aspect of pore pressure and fracture pressure window. Now this actually is a very interesting fact, how you construct your well. So you are always start from bottom to top, and placing the casings, the main thing is that you want now to isolate those formations in order to be able to go deeper. Now, since pressure increases with depth, the formation fluid will enter the wellbore. And to prevent this, as I mentioned before, we have the drilling fluids to provide now wellbore pressure. And as you can see now, if you have overpressure environments, so as you can see here in drilling, you will see that we don't talk for pressure gradient related to pressure, let's say megapascal or psi, but in several times you will see that when we do the pore pressure, fracture pressure window with casing program, we use always the mud weight, so equivalent pressure into mud weight in pounds per gallon. So you can see here is constant, which is the linearly if you see it from pressure perspective, but then again you have the overpressure windows. In the same time, in any case, you fracture now the well, then you start having lost circulation. This is what we talked about, artificial cracking of the formation. So the casing program is a very fundamental aspect of drilling in order to drill those wells safely and reach the target depth. Now the drilling fluids, it's a huge aspect in drilling, but the main now scope is to provide hydrostatic pressure in the wellbore. So this is the primary goal of why we use a drilling fluid. Then it's to transport the cuttings to the surface. So as the drill bit rotates and destroys the formation, it creates drilling cuttings, and those drilling cuttings now, in order to get them up in the surface, drilling fluid is the main, I would say, assistant of bringing them to the surface. But at the same time, you don't want the drill bit to be always in contact with drilling cutting, so this will damage the bit. So the drilling fluid, it also helps to clean the front of the bit. Then is about wellbore integrity. This is, I will talk more about it on a different, I will say, video. Then you have keep solid suspended while circulation. Now, many people have the perspective that drilling is a very continuous action, but in reality is not. Like if you see it from perspective of time, there is many intervals that we don't drill. So when you do connections, so when you connect different pipes, when you encounter problems, when you want to obtain additional information from the wellbore. So in all those circumstances, drilling fluid is not being circulated, it's static. But in the same time, when it's static, you don't want all the cuttings that are in the wellbore to fall down very fast. So that's why it's important to keep the cutting suspended for a while when there is no circulation. Drill bit cooling, drill bit lubrication, hydraulic power to the bit and the motor, and of course downhole information provider. It's the main communication system, the mat pulse telemetry, and this can be obtained only by using drilling fluid. So the casing design, why we actually having a casing. So number one is preventing the formation wall from caving into the wellbore. As I mentioned before, especially for surface sections that are unconsolidated formations, you want to drill them fast and you want to place the conductor casing quickly in order to prevent those wellbore now to collapse. Now the same principle is also for deeper sections. So when you drill those sections, you want after to case them in order to secure from the walls to start failing over time. Then of course is you want to go deeper, so you need to isolate different formations and prevent the flow across the wellbore, providing means to maintain control of formation fluids and pressure while drilling. We talked about this in the previous slide. And of course to protect freshwater reservoirs. This is mostly for the conductor casing. The first, I would say, indicators about how we can actually design our well is by knowing the pore pressure and fracture pressure window. Now, as I mentioned before, after you case, you are actually cement, and imagine that it needs to withstand very high temperature and pressure, and not only for few hours or days, but it's for the entire lifetime of the well and abandonment. And cement integrity is one of the fundamental aspects of drilling engineering, because you want to ensure that your well is safe. So you have here your casing, and then after you cement the well. But when you are cementing, you can imagine now that some casings might be a kilometer long. So you want to ensure that the interface between the casing, the cement, and the cement with the formation is excellent. So you don't have any leakage path. Your casing is centralized in the wellbore. You can imagine if for any case the casing is not well centralized and is much closer to your wellbore, it means that might, in some circumstances, even touching the wellbore, cement is actually not being placed for specific sections. So this creates challenges. What we do is we check it with cement bond logs, how good is actually the bonding between the casing and the cement and the formation. Now, of course, you drill all those meters, and you want also to gain information regarding your formations. Information such as petrophysical. So petrophysicals are porosity, permeability, and several other information, but you can also, and very importantly, is to obtain rock properties. And rock properties, we can describe them as mechanical properties corresponding to rock strength, cohesion, internal friction angle, elastic modulus, and then, as I mentioned, the petrophysical properties. So when you want to obtain now the mechanical properties, we are using a coring bit, and the coring bit allows to drill now a section in which the PDC cutters, as you can see here, as the drill bit rotates, it sears the outer part, and then the inner part is just entering inside the bit in which we're retrieving after in the surface. And then we can take smaller plugs to obtain and to do some mechanical tests. So we have the uniaxial compression test, we have triaxial, and we have also the Brazilian. So those are some mechanical tests that we do in the lab. Uniaxial, it means that you apply stress only from one direction. Triaxial, you have it from multiple directions, so you are giving a confining pressure to your specimen, so the rock specimen, but also axial. And then you have the Brazilian, in which it's an indirect measurement now to obtain the tensile strength of the formation. So for those, you need to create specific size of specimens to do those tests. So rock strength has been specified either in terms of compressive, as we talked, tensile, shear, or impact strength. Now the unconfined compressive strength, which we are obtaining now from the uniaxial compression test, is the most widely used definition and physical quantity that we are using for various applications. Now, when you have in situ stresses, as in the actual drilling process, which is called the confined compressive strength. That's why we do now the triaxial compressions. Now, when you have a rock in different confinement, you will see that the rock, it fails on different limits. So if you see near the graph, so you have the effect of the bottom hole pressure. So the bottom hole pressure, so the drilling fluid, it provides confinement now in the face of the drill bit. And as you can see now, the higher the confinement, you need more stress in order now the rock to fail. And you can see this from the perspective of a drill bit. So this is the cutting force. Cutting force, the cutter, it has several force components acting on it during the drilling action. And cutting depth is now how deep is actually the PDC cutter into the formation. And you see we talk in a millimeter scale, so 0.4 millimeter to 2 millimeter for this experimental rock cutting test. But what is interesting to see is that as the cutting depth, of course, increases, then you're gonna see that the cutting force is also increasing, of course. So the area that the PDC cutter needs to cut is higher, so the cutting force will be also higher. But in the same time, you can also observe that as we're increasing the pressure, the confinement, you will also see that the cutting forces are increasing, and this is what I talked in the previous stress and strain graph. Now, very quickly regarding assessing the subsurface. Now, of course, the technology has been improved significantly over the years, and seismic reflection is probably the first thing that we are doing in order to assess, so to have a first impression regarding the subsurface. So you use, for example, in these circumstances, hydrophones. You have the source, and the source creates now sound, in which this sound now penetrates into the subsurface. Now, the denser the rock, the velocity increases. That's why as we go deeper, the velocity increases. The rocks are more compacted, which means less porous, so they are denser. But what's the problem is that the wavelength now increases with depth, so the resolution of what we can obtain from the subsurface or from the seismic decreases. Another important aspect that we do it while drilling is the leak-off test, or the extended leak-off test, where after you drill a formation, so you can also do an integrity test, you start pumping with closed wellbore in order now to increase the pressure. It gives you different information when the cracks start initiating, so this is the leak-off point, and then how the fracture propagates. Then if you stop pumping, then you want to see how actually now the fracture closing, and depending the test you can do it at a more extent. That's why it's called extend leak-off test. So field injectivity test that fractures rock and measures terrace directly, therefore are regarded as the most reliable technique for determination of the fracture pressure, in order now to start building your pore pressure, fracture pressure window. Now the drill bits, so this is a polycrystallic diamond drill bit. So as the drill bit now is in contact with the formation, you apply axial force in drilling weight on bit. It's a very common abbreviation. And at the same time you provide rotation. And as now you're providing rotation and the cutter's penetrating the formation, it starts to sear the formation. So as it sears the formation, you start having stress concentration in the rock. So you have elastic deformation in the beginning, you go to plastic stage, and then you reach the stress peak, then the formation fails. So you have stress release until now, depending on the fracture propagation in front of the cutter. And then of course, if you see it from the front view of the cutter, you start having, you can see cracks around the rock. Now, as the drill bit now sears the formation, you start obtaining the cuttings, and the cuttings is actually an excellent representation about, of course, the formations. So you're obtaining the cuttings now in the surface with the assistance of the drilling fluid, and then we have engineers in the surface in which they are actually doing excessive analysis of those cuttings to obtain information regarding what formation is it, from which depth it comes from, and if you see some additional specific interesting facts about rocks. Now, of course, it's interesting to say that the other good part of when you use PDC drill bits is that pretty much you know the normal PDC drill cutting, so you can see the normal size of them. So if you're in the surface and you start obtaining significantly different cuttings, it means something doesn't go very well in the wellbore. So those are called the cavings. Part of your wellbore, and we're gonna talk this in another class, it fails for a number of reasons, but of course it doesn't fail because of the drilling action itself. So the cuttings, they have different morphology compared to the cuttings from the drill bit. And this gives you now information regarding wellbore breakouts, which is happening to the plane of weakness in your wellbores. And we will talk in another class about the geomechanics of drilling. Wear line locks. So you have the gamma ray. So after you drill a section, you lower tools in the wellbore and you have the gamma ray that you want to measure the natural radiation, so uranium, potassium, and thorium. Then you have the resistivity, electrical resistivity of the formation, acoustic, so it measures the travel time. Similarly now with the seismic, the denser the formation, the higher the time. And it can give also an indication regarding to rock strength. So there is a correlation between acoustic time and UCS. Then we have neutron density to see the concentration of hydrogen, caliper to observe now the wellbore size. And then we have also the nuclear magnetic resonance, which is an NMR for determination of the pore size. So those tools are lowered now in the wellbore with cable, and when you lower them, then you don't actually measure something, and you start measuring when you start pulling them out at the surface. So regarding the subsurface stress field, very briefly I will talk about it. So this is your wellbore, and depending now of how those formations are actually formed, depending on the stress field, which can be from tectonics and other kind of sources, you have your SH max and you have your SH min, so your maximum and minimum horizontal stress. And in the same time, because you have now a drilling fluid in the wellbore, it actually also gives stress in the formation. So that's what I talked in the beginning, that drilling fluid also assists on stability of the wells. And this has to do that as you're increasing the mud weight, you start having greater radial stress in the borehole, and this actually, now we will talk in the other classes, it assists on keeping the wells stable. But when you look at it, now if you had the caliper log, you could actually be able now to observe the breakouts. So this is areas which is on the minimum horizontal stress, that the wellbore is larger, and we will see that depending now on your mud weight, this will have different impact. And of course it's important all those things to obtain the rock mechanical properties. So we do an extensive analysis for the friction angle, pore pressure, minimum and maximum horizontal stresses, vertical stresses, because there are areas where are very challenging to drill purely because of the subsurface stress field. Now, directional drilling, of course the wells are not vertical, so we can actually control the trajectory of our drill bit in order now to enable us to drill several wells from a single location at the surface, in order also to reach inaccessible surface locations. For a reason, don't want to use an offshore rig. You can have multiple target zones depending now on the applications, because it's very challenging sometimes. You might need to abandon a specific section and then sidetrack and re-drill, or to drill a relief well, salt dome exploration, and fault drilling. So to give a small terminology about directional drilling, is controlling the direction and deviation of the drill string in 3 dimensions with the assistance of mechanical equipment. So if either those equipment are the positive displacement motors or rotary steerable systems. Now from downhole measurements, as I said, we have big technological advancements. So you have the logging while drilling and the measurement while drilling. The logging while drilling, we use it to obtain some formation properties, as I said, gamma ray, resistivity, etc. And then the measurement while drilling, we have it in order to obtain what is our inclination, what is our azimuth, in order now to control, with the assistance also of the LWD, the trajectory of our well. We have a mud motor, where this is what we talk about, the hydraulic power to the bit. So drilling fluid, it comes inside the mud motor, and you have now the rotor and the stator to provide now rotation to the drill bit, but also to be able now to control the tool face orientation. Then we have the rotary steerable systems, again, very sophisticated systems, point the bit or push the bit methodologies, and this we're going to talk in another class in more details, but those are actually the equipments that we use for downhole measurements and geosteering. Now the real-time monitoring, you need to think about it from perspective of an F1 car. So this is an F1 car, and you can think that the racetrack are now the formations drills and the trajectory. The tire type is your drill bit, the steering is the driller or the geosteering system. But the telemetry now in those kind of systems is very high. So you have around 500 Hertz. So this is your sampling frequency. In drilling, actually, we get 0.1 Hertz. There is now some technology that you can provide real-time downhole measurements rather your mud pulse telemetry. But the main difference now between the drilling side monitoring, so we monitor all kind of variables, weight on bit, torque, pump pressure, rotational speed, hook load, block position. We're going to talk this in another class. But the main difference is that for the F1 car, you can actually also see it. But when we're drilling now 4-kilometer wells, you cannot really observe what is happening. So you are really putting your trust on the data to analyze them and taking decisions on real time. Challenges now regarding the geothermal. I will go very briefly. This should be another video. So this is now the geothermal gradient at 5 kilometers across Europe. You can see that there are areas with very high temperatures, so 240 degrees, compared to other areas which they are normal gradients, which is 80 to 100, 120 degrees, etc. And geothermal is actually start picking up very significantly all over the world, since it's the renewable energy source. But still, in order to reach those depths, again, is related to drilling technology. Now, of course, the deeper you go, the hotter the rocks, the stronger the rocks, the different the entire system. So we use percussive drilling. This is some new technologies. So it creates the drill bit now with a fluid percussive action in order to drill harder rocks. We have laser drilling technology, we have plasma drilling technology, and of course those are very fascinating technologies that hopefully, will push the boundary and be able to drill those deep wells, but of course still requires a few years until those technologies be commercial. Now the PDC bits, they are also, the action is the same, but we start having technologies where you can control your depth of cut over time. The cutters are actually rotating in order to reduce the contact time for a specific point. So those are adaptive bits or rotating cutters bits. We have the Chimera drill bit, which you can see now is a combination of a PDC bit with a roller cone bit. Then we use metal to metal motors in order, when you drill deeper reservoirs, temperature higher, the elastomer inside will create, it's gonna be easier to deteriorate, so the efficiency of the motor decreases. So there are very many innovative technologies that can be utilized to enhance now the drilling efficiency in hotter and harder rocks. And this is gonna be a new chapter of our coming up videos. And as you go deeper, of course, the temperature is changing, so your drilling fluid properties, the rheological properties are changing. So you can see that as the temperature increases, the viscosity of the fluid is significantly lower. Several problems can occur because of that, such as low capacity of the cuttings now, lower wellbore stability, etc. And of course now those formations are naturally fractures. So this is an image, this is a pencil, you can see the fractures now on the rock. So you start having big problems regarding loss circulation when you're drilling those wells. For future videos now, I was planning to create a video on drilling fluids and hydraulic, PDC drill bits and mud motors, directional drilling and torque and drag modeling, geomechanics and assessments while drilling, downhole and rig sensors and drilling data quality, and lastly, drilling data analytics and monitoring. I still haven't decided the way that I will create the videos. Please, you can leave on the post a comment which you would be more interested to see, and I would be happy to create additional videos. So thank you for watching. I hope it provides you a little bit better overview about drilling, the challenges we are facing, the equipment that we are using, and how actually it enables us to explore our planet, drill to obtain the energy of our planet. So thank you very much, and see you next time.